it would help if I spoke and I wasn't muted. So today is going to be very different from my other streams. My other streams, I play video games. This one, I wanted to do some software development. Why not? You want to see some Rust? This is, I can't even say this is as far as I got. This is what Cargo puts in by default. So you can just run it. There it is. It ran. Cool. All right. I did set up some music. I'm going to turn that down even more just in case. How loud is it? Start. Oh, that's a little too quiet. All right. I pulled all this off of the YouTube music library, so better not get any trouble for using this stuff. It's what it's there for. Let me know if you find it annoying. I don't mind turning it off. All right, so I was going to make a Chip8 emulator. And that is a... I don't remember the exact terminology, if it's an interpreter, if it's a virtual machine, or if it's an emulator. And it's not really an emulator since it's not emulating an existing system. Virtual machine or interpreter. But that doesn't really matter for the implementation. Essentially what it is it's a set of instructions, it's a memory layout, and it's a display. The Chip8 was very old, created for one of the Cosmac computers. Cosmac? In the late 1970s. So it's kind of old. And it can basically do, actually I should have, yeah, here's all the opcodes. There are 35 opcodes. It can do jumps. It can skip instructions based on some logic. It can do all the simple math you need to do. And that's about it. It's very simple, very straightforward, and that's why I'm doing it, because I'm also very new to Rust, and I'm kind of using this as a way to learn it. So I'm not showing this, but I also have my browser up in another window with a bunch of windows open, or tabs open for Rust documentation. I also have some other stuff here. Oh. It's skipping around kind of annoyingly. Yeah, so we've got a whopping maximum 4 kilobytes of RAM. The original computer this was written for, I believe, had 2 kilobytes, so even less. This is kind of how it's laid out. 512 bytes for the interpreter code itself for the Chip8. You start at hex 200 for the ROM, and that's in quotes because while games and stuff are often distributed and they call themselves ROMs, memory is not read-only in the Chip8. The initial load will be whatever the file is, and then that can all be rewritten later on. In fact, that's pretty common to do. Since space is limited, you can rewrite memory onto your program. And the tail end of memory had call stack and internal variables in the initial implementation, as well as everything calls it display refresh. I'm not entirely sure what that is. Maybe it's just the bytes for the next display. So my thought after reading all that was, we'll keep it simple. We'll make 4K of memory. We'll load the memory in at 200, start the program counter at 200 hex, and go from there. So it only had 18 registers, 16 of which were generic data registers. We have the program counter, which not really register, but something, just keep track of, because it's not explicitly stated in a lot of the documentation how the program counters interacted with. 16 1-byte data registers, the last of which is generally used as a flag for some operations, for instance, overflow or underflow or borrow for add and subtract, as well as shift left, shift right. And one 16-bit, technically 12-bit, 12 bits are only used, address or index register, used to load and store to the RAM itself, since the data registers can't hold a number large enough to access all 4K. This isn't too important. Stack. We can just make our own stack outside of memory, unless we want to really be, what would you call that? Really want to match the original implementations closely. It also had two timers, a delay timer used for general timing, and a sound timer, which lets out a beep when it's non-zero. There's no music. There is a single tone used for everything. The timers operate at 60 hertz, so it counts down 60 times a second. You set a value in either timer, and it starts counting down 60 times a second. So the inputs are, oh, this isn't formatted right. The inputs are, let's go fix that. There we go. Hexadecimal in a sort of, I think it's a kind of a weird pattern around the edge. Like, I see sort of what they're doing, but whatever. It's hex, and as long as we know the layout, I'm probably not going to be writing any ROMs for it, so whatever. I just need to be able to read the input, and that should be fine. Graphics, it's monochrome output. I forgot to write down how big the screen was. That would have been good information. Drawing is a bit weird, and it's also how collision detection is done. If one sprite unsets another sprite's drawn value, a collision is detected. So every time you draw a sprite, you just do an exclusive OR of every pixel, and if a pixel is unset by that operation, it's a collision. And here are all the opcodes, all 35 of them. We will only be accounting for 34 of them because, oops. Oh, that's how that works. That's neat. Because this first opcode here is to execute machine code, which, well, one, it would make your ROM non-portable, which was kind of maybe a consideration, maybe not, I don't know. And two, none of the Chip8 programs would even know about x86, let alone x86-64, which would be the machine code that would run on a modern computer. So yeah, that's kind of a summary of the Chip8. That's what we're going to make. And I'm just honestly going to start hacking at it. So a good place to start would probably be to, let me think, load a program from, I mean, we'll just have some static bytes that will load from, so we don't have to load from a file just to test out. So we'll load some static bytes. Turn it into opcodes, and then print out those opcodes. That's a good place to start. And then from there, we can go and actually do another step of, okay, for each opcode, it does something. And actually, we can even do that as part of the first one. We'll just have it do a print of itself. So let's get... Oh no, just by hitting enter, everything's gone wrong. Interesting. Maybe I shouldn't have updated so quickly. What's going on here? Do I need to update the rest tools? Well, okay, so that's not going to be helping us. Wonderful. Where was I? Oh, right. Let's come up with what we want to do, and that will be load a value, skip something, and then 2 instructions after that to prove that we've skipped it. All right, so where's load or store, I should say. Store and delay timer. Oh, I just kind of wrote it like that. That's helpful. Okay, 6x NN. So N in data register X. So there. Oh no, you just declare it like this. And we'll store its hex. We'll just store FF in there. This is U16, and there will be 4 of them. That's not where I declare that. Oh, wait. Duh. Like I said, pretty new to Rust. So set data register. Then skip if its data register is equal to something. What was that? 3x and n. So the next one will be 3. We did it in 0. Equals f. All right. Okay, and we'll do 2 sets and then inspect, and that's how we'll determine that that instruction works, and that we're loading and doing things in the right instruction. So if it's wrong, we'll store 0. We'll store 0 in 1. If it's right, we will store 0. No, we will store FF in 1. Actually, 0 is not helpful because it might be initialized to 0. We will store 1. There we go. Not do. It's not really a jump, that's a skip. So we're not jumping to an address, we're just skipping the next instruction. Skip that, and then the one that shouldn't run is there. Haven't done a single thing towards. Cannot find macro print line in scope processing. That's great. Wonderful. I wonder if there's something. Nope. No? Weird. Let's just try cleaning it. Yeah, I think there's just something scary with the new version of Rust and the tools in VS Code, because this was working when I messed around in here a little bit before. Oh well. All right, so before we can even... Actually, no, we can do the opcodes first. That would be... Well, technically it doesn't have to be public at this point. What's wrong? Oh, just gonna complain about that. Sure, why not? We've got our enumeration. We need to get down to at least 6. I kind of want to put these in order just to have that. So we will decode that opcode and then, I don't know, throw in panic or something. So X and N. Wait, no. That's wrong. That should just be 3 N's. So this runs arbitrary machine code that starts at address NNN, which would be some random address in memory. These might be wordy. Maybe I'll change that later. But for now, eh. 16 to fit that. Next is clear screen. Oh wait, this doesn't take anything, so we can just leave that. Oh, EE, return from subroutine. Now I'm sure there's Rust docs, and I should honestly be using those. I'll go look that up after I type this out. Don't like using return, but at the same time, it's return. And it is namespaced in opcode and it's capital, so that's fine, probably. So, going to comments. Well, okay, just 3 slashes, supposedly. We'll make them generated documentation. We'll see about that. Okay. Turn next to jump to address, which is 1. Yeah. Doesn't document anything. It's getting there. Subroutine. Oh, I see. Right. Skips. So first is skip equals. For a constant. Think I need to use usize because I'm going to use this to index an array. Yeah, well, wait. All right, this is against the constant, right? Value to compare against is a U8. Oh, that's why it's yelling at me. We're getting commas. equals the constant. Right, then skip not equals. Wait. That's skip if equals constant. Yeah, no, that's right. Yep. We'll say equal, not equals. Skip equal constant, skip not equal constant. Same thing. Register the value. Five XY0. I can spell. That's for comparing registers. Simplify these a bit with some math symbols. Uh-huh. All right, we need one more before we can even think about messing with this. That is 6xnn. Should that just be store? No, because I think you could store directly in memory as well. Yeah. Store, we'll say store register. Register, and we need the value. So kind of some repetition with some of these. A lot of them have a register and a value, but that's just kind of how it is. Okay, and with these, we can technically use the ROM that we have here. I mean, we need a lot more, but should work when we put the code for it in. All right, I'm gonna be bad here, and yeah, I can do that. I'm going to put in something just self. Just to force an exit while I'm testing stuff. And I'll call the exit delete this, so I know to delete it. All right, so we can just loop. All right, and we're Chip8's an interpreter, but we're kind of doing things like a computer here, or a CPU, I should say. So we're going to go with fetch, decode, execute, because that's what you got to do. You get the opcode, decode the opcode into instruction, and you execute the instruction. And you just loop over that forever. All right, and let's put our completely invalid opcode in here to have it exit afterwards. All right, so we need a function to fetch. Which will take wait, that's backwards, isn't it? Wow. Our program counter and our memory, which right now, this isn't valid, like 5. CPU 16, 5. And it will return opcode that is U16. Really nothing fancy here. Let's see. How do I want to do this for the program counter? Increment after fetch. Yes, that makes sense. This is where we're probably going to run into our first borrow checker issues because I don't know how this is going to work. That's valid? I thought it would yell at me for... Or maybe U16 could just be cast to U size. Okay. So we're definitely going to need a reference to this since we're incrementing it. Wait. No. That won't work. Even if we have a reference to it, will it actually increment it? Only one way to find out. Fetch. Oh, we will... start at 0, which isn't quite what we want to do, but whatever. We'll change this later. Opcode is fetch ROM bytes. I'm sure there's someone watching this screaming at me that this is all wrong, but you know what? You're not doing it in the chat, so I don't hear it. And this would return an actual opcode. Or maybe I should call it an instruction, since the opcode is the X, or the numerical value. Call it an instruction, because at this point it's not that numerical value anymore. And this is just going to be a big, ugly match statement. Or is it opcode match? I don't remember. Must match. Let's look. Nope. Match value. Excellent. So our catch-all, which I should put in here, is going to be invalid opcode. If we run into something that doesn't match anything else, it's an invalid opcode, and we'll just store the opcode in it so we can inspect it. So this says opcode 3 times in a row, and that's fun. Ah. Can I use instruction? Get rid of that. No. There's a way to bring that in scope. No external crate. Where does it start? Guess I can just drop instruction on everything. It's a little ugly, but whatever. Okay, so what do we have for opcodes? Let's start with the 2 specific ones with 0. So 0 be a 0. Let's clear screen. EE is call, right? No, EE is return. Obviously, you need some actual data for a call. All right. Anything else? 2 0 FFF is easier to just jump to this. Execute machine code. And that address is... Oh, that's right. I have to do equals. Exclusive one would be nicer, but I think that's not finalized. Whatever. This is the opcode bit masked with that. And it's not going to get weird until we have to do U8s. All right, 1. the address. So we'll do the same thing here. Jump. Maybe I should do jump absolute because I'm pretty sure there's a jump relative. Let's fix that right now. Jump absolute. And the address is the same exact thing. Two. It's gonna use the same logic. This is call, right? I already forgot. Call subroutine. Address is opcode. Wait. I'm smarter than this. Supposedly. Okay. Three. Skip if Vx equals a constant number. Is going to be a little different. Skip constant. So register is the second byte. Which means the opcode, mask it, and then shift right twice. And I guess that's fine. You know, sometimes I can spell. The value is the rightmost byte. Oh, sorry. The opcode, or the register, is the second nibble because it's in the first byte. The value is the second byte, and there. How do you split a U16? Can I just cast it to a U8? Let's see what returns a U8 on here. Okay, I'm getting a bunch of stuff on the side. Oh. This is big endian, I think. So that should work. 2 BE bytes. And we get the second byte. So opcode 2 BE bytes. We want byte 1, which is the second byte. Because we index by 0, like you're supposed to. These are all pretty similar, right? Okay, this is the exact same, just a different instruction. And this one is going to be weird. Okay. This is going to look ugly. I should probably format this nicely some other time. And technically, we're not getting everything because this instruction always ends in a 0. So we'll let it fall through to the invalid opcode if it doesn't end in 0. Skip equal register X, which is going to be... Why did I shift this right to? That's not the right amount to shift it. It needs to be shifted 8, I believe, if I'm counting right. Anyways, so this is register X. Register Y is going to be similar, actually. Opcode. Shifted right 4. Because there's 4 bits per hex digit, yes. Okay, one more, and then we can start actually trying to run this thing. Sort of. The little tiny cobbled together subset that is here. Alright, 6xnn, store nn in x. Which is going to be a lot like this. Only different range here. Because we're using the same register location in the opcode and the same bits for the value. Yeah. Okay, that's decode. So code. Wow. There we go. Decode the opcode. And execute. We have to write. But that's just going to run. Execute. The instruction. Return nothing. Okay. I mean, here we're just going to do a match statement again, aren't we? Clear screen. Okay. Wow, this is all sorts wrong. Okay, print line, macro. How'd that get in there? All others. Actually, no. We can do an exhaustive list because it's a enumeration. Exit. Exit, delete this, right. Is there a... I could panic. It would be not so smart, but I could panic. Panic abort. There's gotta be a better way to do that. Last exit. Search for that. Exit in process. Terminates the process with the specified exit code. Will never return, will immediately terminate the current process. Exit goes past the underlying OS and will be available for consumption. Excellent. That's even better. That's in process, so we'll use std process. What is wrong here? Process exit. Exit successfully because that is expected. It's going to fail to build because I don't have all the things there. Whoa. Found a pool. Pretty sure and is ampersand is the bitwise and, right? And then right shift. Oh. I probably don't have the right thing for right shift. That's probably it. Just right shift. Right shift operator. Right. Is 2. Yeah, because this is all... Whoop. I didn't want to delete all that. That's all greater than, which is not what I want. Try again. Expected U size found U16. That's what I'm expecting. Okay. Is there a graceful way to do this, or do we just use as? Let's see, it should have a trait for that if we can do as safely, right? From U16. Yeah, that'll be fine. I don't think I have to do usize.from. I think this will do the same thing. Expected usize found U16. Oh, 8 as usize. It's just turning the 8 into a usize. Wrap it in some more parentheses. And that's getting to the point where I'm just going to copy and paste that. Probably could have also done find and replace. Expected usize found bool. Oh. Shift right. Actual operand for that as usize. Nice. Cannot use plus equals on type and U16. Can be used on U16 if you dereference it. Okay. Are we getting into borrow checker errors here? Expected 16 found integer. Consider borrowing here. Ah. Yes, I have to explicitly borrow that. Mutable. Expected type found keyword. Isn't that where you put it? You put it on the type, right? Guess not. This is probably also terrible. This is, yeah. Expected 16 found. Wait, let opcode equal. Oh, here we go. Expected U16 found reference integer. Ah. Explicitly make it a U16. That ought to fix that. And give me a brand new problem. Expected U16 found reference U16. Yeah. Unreachable statement. Everything after that, yeah. Get rid of that. That's fine. Type U16 cannot be indexed by U16. Ah. That's fine. This can be a U size. I don't know why I was making that U16. Hey, it built. Convert the identifier to snake case. Exit, delete this. What? Should have a snake case name. No. Unless it's not actually. Is that what's going on here? More, I don't know how to actually put this into the... Oh, cannot compile. Yep, did not cover everything. Perfect. Now it's actually, yeah, okay. Now I really want to know how to do that because putting instruction everywhere is tedious and unreadable. That might be it. So if I get the same error, that worked right. And I think I did. Yep. Not covered. Oh, that's much more readable. Okay. So I'm just gonna have everything print itself. I don't know why it can't find all the standard macros, but whatever. What's wrong with execute machine code? Oh, it has, I need to bind the address. And now I actually need to know the formats. Oh, format. All right, simple enough. Is there a way to dump it as hex? So decimal is X. You know, I do kind of prefer uppercase for... Oh, look at that. Yeah, uppercase for hex. The reason I use lowercase letters in the documentation up here is that it's clearer that they are, they're not constants. So, yeah, so something like 00E0, the E is the hexadecimal E. Whereas here, the N's are, I mean, hexadecimal doesn't go to N, but it's more visually clear that they are not part of the number. The literal number. Register the value. I'm just going to keep those the same. Oh, I got temporarily disconnected there. I'm not sure for how long, actually. Fortunately, it reconnected. Okay. We're filling out all of the instructions to just print out what they are. That way we can run this thing and see it, and then, well, spend like 10 minutes going through all of the mistakes I've made. And I'm sure there's someone watching who can tell me all of the mistakes I'm making. Wait, I didn't rename this up here. That's not skip equal constant. That is, what's that? 6 is store. Which, right, I copied that because it had the same parameters. And one last one, which is store. Oh, and invalid opcode. Forgot about that. I forgot to decode my exit instruction. There we go. Or let's register into value. Store. No, we can still do this. Store in the X. We'll just reverse it. Value. Register. What's wrong with store? Cannot find struct store in this scope. Wait. Oh, store register. That's right, because there are other stores. Let's delete this invalid opcode. Execute takes an instruction and executes it. And yes, I could call by doing execute and then call the function decode, which calls the function fetch. But whatever. I never said I was good. No arguments given. Oh. Compile time. Move this. It is mutable. Well, we'll see how bad this is. Cargo run. Yeah, that's what I thought. The function's getting a copy of PC. It's incrementing that, but then when it gets back into the loop, PC is still 0 because it copied into the function. It didn't pass the reference. And here's where I actually need to, understand what I'm doing. Pass the reference in. It's mutable, and this is reference to usize, and then we dereference, increment by 1, slice indices, type usize, or ranges of usize. Type U16 cannot be indexed by, and usize. Right. I mean, why mess with this when I can just do that? And figure it out later. Oh, and it doesn't need to be referenced. Store ff in v0, skip if v0 equals ff, store 1 in v1, store ff in v1. It works, as expected. All right. That's great, actually. I mean, except for all these errors that it thinks there are, but I think the plugin just needs an update, hopefully, or I just need to restart it. Okay, so the next logical step is what's the next logical step? Oh, to split out this stuff into a module. The Chip8 stuff. And we can have the actual, computation in a module, maybe put the graphics in a separate module or in the same module. Yeah, we'll figure it out. But yeah, a module for Chip8 things, which requires me to understand exactly how the module file hierarchy works. Okay, I can just I think this will be small enough where I can keep it in one file, and if not, we'll split it up again. So new file, chip8.ers. take these instructions. This is going to break the compilation. Actually, once we move everything out, oh no, this'll decode should be part of the CPU stuff, so that can probably go over. Yeah. Fetch, which we'll keep public for now. A lot of this is going to get repurposed for something else, because we do need to actually keep track of what did I press? Oh, there we go. We do need to keep track of the CPU state, which we're not doing right now. We're just printing out what the opcodes would do. We need an actual CPU, the data for the CPU to emulate, which we will make. Chip8. Okay, so the Chip8, this is where we actually put data that we're going to use. So we'll have the program counter in here, and that's going to be a U size. That'll be fine. We have the general purpose data registers, which are V, and that is an array of U8. There are 16 of them. We have I, which is the address register. It's a U16. Could that be a U size? It does need to index into the memory. I think I'll have it be a U size. So we have memory. That is going to be can we make an array that's 4K long, or is there a limit to static arrays? You know, it'll be a vector. It's going to complain that it can't find vector. Okay. Timers. So we have delay timer, which is a register, it's U8, and sound timer, also register, U8. So this is a vector, and I believe you can give it the array syntax. So that'll make a 4K vector, which means technically we can give more memory if we want. But you know what? I'm going to just to see if it's possible. It's not complaining right away. But there are 24 errors here. Both of these, yes. Why does it think something hasn't been saved? Whatever. Build it. One warning. One error. Use of undeclared crate or module process. Oh. That doesn't need to be there anymore. That needs to be in here. It runs still. Perfect. The documentation on here. I mean, these are pretty straightforward. Delay timer and sound timer. But hey. All right, so now, instead of so instead of need a way to load the ROM. Well, we should probably implement new for Chip8 just so we don't have to set everything. Function. Take anything? No. So there's going to be C is 200. B is 16 zeros. I 0. $40.96 zeros. Delay timer is 0. Sound timer is 0. Oh. There we go. All right, so new gets us a Chip8. And that's where all of our data is. Which means these functions should operate on Chip8. And then we don't need to pass these in. Yeah. So this comes out, or this goes into sample Chip8. We have self. Um, just self dot. Okay, self dot mem, self dot. So do I need to make those mutable? PC might need to be mutable. Maybe I can just mutate. It can just mutate itself. Right. So let commit by one. Then return next op. This is probably wrong. Call it Chip8 CPU. All right, so we'll make a new one. And then this will be CPU.fetch. And we pass in nothing because it doesn't take anything. And it left it. Okay. We don't mess with that. We don't need that anymore. We will need ROM bytes. Let's see what happens. Doesn't even work. Okay. What is this? Expected U16, found U8. Right, because it needs to read 2. Alright, so I need to convert 2 U8s into a U16. Oh boy. Oh, but there's a way to do it. Okay, I think Rust has array slices. Right, this is, we'll make it explicitly use 16. That way it yells at us. All right, it's not dot, it's going to be 2 colons. Does it compile? No. Found a slice. Alright, so I can't do it from a slice. Because it doesn't have the size of the slice. Right. Okay. So in that case, we will make it 2/8. All right, program counter has to go up by 2. Is this even valid? Am I just writing junk? Expect U16 found. Oh, right. Turn. Self is a reference, so the data it refers to cannot be written. Okay. Consider changing this to a mutable reference. Oh. There we go. Cannot borrow as mutable. Fantastic. Wait, what? It was not declared as mutable. Oh. Yeah, we're going to be mutating the CPU state. Shocking. I know. Panicked. Index out of bounds. Execute machine code. Oh, everything is... Yeah. Oh, wow. It just dumped out all of those. Great. So it sort of worked. That's because we don't have any actual instructions in there. All right. Let's get decode and execute in here. That should still be fine. I guess, you know, it would let us decode and execute arbitrary functions if that were ever a thing we needed to do. You know, for debugging. CPU.decode. Then again, this loop should probably just be... like, we should have like a step that CPU does. And inside that, there's fetch, decode, and execute. And those are no longer public. Only step is... yeah. But whatever. It's fine. It's all there. The next thing was we need to load the ROM at address 200. So what do we take in? Do we just take a slice? Doesn't return anything because, well, It's just loading the ROM. I guess we can tell it where to load. And this is a self, mutable self, because we're going to be writing memory. And mute self. All right. So first off, self.pc equals address. And then what do we have available on the slice? Does a slice have a length? Okay, yep, they have a length. So actually, do they have a nice iterable function? That would be great. Or we can just loop over it. So is there anything weird about Rust for loops? Loop for is it inclusive? It's not. Excellent. So self.men C plus I equals ROM I. ROM. Ooh, that's nice. And ROM bytes. Address 200. Oh. Expected U8 found, U16 5. Okay, we need to split this into after fixing it, can I just pass in ROM bytes? So these need to be U8. These. This is really just for testing it out, so this will get deleted at some point. It doesn't matter if it's really ugly. Okay. And that made more problems. This is an associated function, not a method. What? Oh. No, these should be... Not that they're going to be exposed for very long, but expected array, consider borrowing. Sure. Expected array with a fixed size of 5 elements. That's because I forgot to change that. There are 10 now. Hey! It worked. It's gonna bug me about unused stuff. Okay. So it works now. Well, it's back to working. I don't know how to... what to say about that, honestly. Back to exactly where we were, but now this is loaded into an actual structure and running from there. I haven't commented many of these lines. That'll be a problem later on. What was next? Oh, actually doing things with instructions for some of them. So what are we actually using? We're using store. So store value in register. What this actually should do is... All right, self is mutable because some of these operations change it. Self.v register equals value. I want to derive debug, but I don't want to dump out the entire memory every time. Or I want debug. I could implement debug. Create debug. Take some formatter. Formats the value using the given formatter. I may need to see let the debug tree. Don't want to derive debug. Oh, okay. There's a really good example. We need format. So impl format debug for, wait, this has to be in a separate block. Why am I in the general impl block? Why is that all in caps? Whatever. So let's see, this is, well, also and self. Mute formatter, yep. This returns a format result. What's wrong? No, nothing's wrong. Chip8 CPU. Maybe I'll bike shed that at some point. Yield. Get out of here, examples. See. Oh, name. Ow. Yield B is an array, so self name value is a debug format. So can I debug list? What does debug list do? What is, that's the formatter. Okay. Bring that up. Debug list. List-like structures. Okay. Do arrays have an iterable on them? Or you know what? Maybe it's smart enough. And self.v. Well, if it's not, I'll mess with it. If it's not. I is capital. No, it's not. And self.i. We're not doing memory because that's just a giant chunk. Delay timer. Delay timer. Sound timer. So that's sound timer. Okay. So now after each execute, or before each execute, print line debug self. Perfect. Expected enum result but found debug struct. Did I miss something? Oh, finish. Hey. It does know how to print it out. Nice. Can I give this a format? In field? Debug struct. Turns debug struct. This has field. Self string value. Value is a debug. What is a debug? Oh. Format is a formatter. Formatter. What? This is debug. I want formatter. Well, it does want a, it wants a debug. Oh, can I do format? Can I format this? As upper hex. No. Found string. Okay. Okay, format args is what I'm supposed to use there. What exactly does that do? Is that it? No, that's not it. Format args. Yeah, what? Well, they're passing it as a reference? Okay. All right then. I just need to look back at actual formatting because okay. That. And you want 2 digits. Nope, you want 4 digits. Wait. Can I even go to 4 digits? We have 4K. Yeah, whatever. How's it look? It's not printing out 4 digits. Because I need to tell it to. 04. Or I don't know what I'm doing, which is extremely likely. And we do the same thing for I. And V I'm going to leave alone because, well, not going to mess with an array. What was I doing before all this? Oh, more, I was about to say, why did it not skip? But I haven't actually put that in there yet. Okay. So we have store. Skip, store, store. Oh, so we only need to implement skip for that crappy little program. So skip equal constant. So at this point, okay, yep. Yeah. So the program counter has already been incremented to the very next instruction. So to skip, we just increment it again by 2 because we're dealing with bytes. So if self dot b register equals value self dot c 2. What's wrong here? Oh, I don't need parentheses, and it doesn't want me to have the parentheses there. Readability be damned. And now it doesn't write the 1 in that step. Excellent. This is great. And it only took 2 hours to get here. We're doing an execute, which is why it's off by 2. Because this is technically the instruction at 200, not at 202. That's great. Okay, so we can also do some more stuff. Let's set it to a skip not equal, which is skip not equal. Just swap it for a 4. All right, skip not equal, and we'll implement that. Which is literally the same thing, just not equal. I don't think that worked. If E register does not equal value, PC plus equals 2. Oh, I also need to change the value. Because if it doesn't equal the value, plus equal 2. So we'll load 0, 1 to the register and run. There, now it skips it. Skip equal register. This will actually be a little more interesting to write the test run for. So, I mean, this is going to be easy. If self.v register x equals self.v register y. Yes, I could have just done x and y, but actually I might. Self.pc plus equals 2. Where are these? Okay, they're down here. Nah, I'll leave them. It's explicit that they're registers. Alright, so now I want to do that. So we store, that's equals, right? Skip equals register. Yes. So we store FF in register 0. We also store FF in register, not 0 again, register 1. Down here, let's set these in register F. All right, and skip. So it's 5, XY 0. Five, register X is 0, register Y is 1. That should be 0. Cargo run. 10 elements, but found 12. We'll just let it figure it out at compile time. Expected slice UA, found array, UA 12. Wait. What? Why don't I just do this? The vector of U8s. Expected one of that, or that. Well, that's because I put this on the wrong side. T. Yeah. No. What? Oh. Can I make a vector of... Yeah, it's fine. What the heck? Okay. So... does nothing before executing. Alright. Store. Since they're both stored. And then we skip. And then set it. Yeah. Excellent. Perfect. What else do we have in here? I think that was pretty much it. I don't have a stack. The stack, should we do it as a pointer and go backwards from the last bytes, or... Nah. Stack is going to be an array. Wait. I need to put it in the field. U16s. How many do we want to support? Let's say 32. You can nest 32 calls. I think 12 was the maximum on the original implementation, just because of memory concerns. So 0. Where did I touch something? 0. 32. Put it in the debug. Well, we will put the arrays at the end. Did I? I did. Wow. Okay, yeah, now there's just an obnoxiously large stack in there. Of course. Let's derive debug. See what happens there. Why did I put another one? Yep, that's what I thought. Well, something. That would be nice to have like a visual of, but that's something advanced. So we'll keep it with the custom implementation here. So cool. Do do we want to put in another instruction? Add bx to n. Am I sure it's not the other way around? It's probably the other way around. Because it doesn't make sense to add it to a constant. All right. So let's put that here. Sorry, so we'll store ff in there. Well, we've kind of shown that that works. So we'll just do the next one and then the exit instruction. 7xnn. So 7, 0, 2. Ooh. Let's add F to it. And we'll see the flags work. Maybe. Because I have to do bitwise adding here. Which means I need to detect overflow. Ooh. Is it possible? There is an overflowing add. Huh. That makes this a lot easier. Okay. All right, so we need to put the instruction in, which is after store register, have add constant. Oh, there's no carry in this one. So VF is normally used for carry and borrow, but we don't need to account for that for this one, so we will just overflow add, and I assume we'll want to do the wrapped value for the add, so we'll just do that. First we need to decode it, so everything in the OX 7000 range will be add constant. And we will take the same exact code, which, I mean, I might just split that out into a function because that would be useful. Okay, there, and now we add execution. Well, if you do a normal add, probably implements add. Yes. Read more about add. Okay, so it adds. It just does plus. Okay. We will just add with plus. And we'll see what that does. Panic. Attempt to add with overflow. Overflow add. Back. Oh, that returns a double. Tuple? To play? There's the first one, right? Yes, first one is the value. Do it again. What? Unexpected token. I deleted the comma. There's associated function overflowing add. There we go. Okay. XFF plus F is 14. Yes, that makes sense. Because those are still decimal. I don't want to go through and make them all hex. All right. Well, that worked. Set the register. Execute it. Oh, right. The last execute was exit delete this, which will process exit. That's why it was caught there. Okay. Wonder if I should put that debug on fetch. Because then we actually see the state it's going to execute, which probably makes a lot more sense. Well, let's take a look. Wait, what? Are there only 3 instructions? Yes. Oh, but not the process. The program counter is at the spot where it's, yeah. Yeah. Perfect. So I got up to adding a constant. I'm sure this will be reformatted a bunch of times, but I think for now, I'm going to be done. Because it's been a while and made it pretty far, actually. Got a lot of opcodes working. I mean, there's still the entire display to handle. But yeah, I think it looks good so far. Of course, everyone has their own opinion, and I'm sure a lot of people who will watch this will hate it. Thanks. I hate it. All right. Well, thank you for watching. That's going to be all for now. And I will see all of you later. Goodbye.